Welcome to this problem-solving session. Today, we'll be tackling the maximum subarray problem, which is a classic algorithmic challenge and highly relevant in coding interviews. This problem focuses on identifying the contiguous subarray within a given array that has the largest possible sum. Let's dive in and explore various approaches to solve it. In this problem, we are tasked with finding the maximum sum of a contiguous subarray within a given integer array nums. A subarray is simply a portion of the array that consists of consecutive elements, and it must contain at least one number. For example, in an array 1, 2, 3, valid subarrays include 1, 1, 2, or the entire array 1, 2, 3. Our goal is to identify the subarray that produces the largest possible sum of its elements and return this sum as the result. The input is a single array nums, where each element represents an integer, and the output is a single integer representing the maximum sum of a contiguous subarray. To help illustrate the problem, let's look at a few examples. In the first example, the input array is -2, 1, -3, 4, -1, 2, 1, -5, 4. The subarray 4, -1, 2, 1 produces the largest sum, which is 6. Thus, the output is 6. In the second example, the input is simply 1. The array contains only one element, so the subarray is the array itself, and the output is 1. In the third example, the input array is 5, 4, -1, 7, 8. The subarray 5, 4, -1, 7, 8, which is the entire array, yields the largest sum, which is 23. This is because including all elements produces the maximum sum in this case. Additionally, we must consider the constraints. The length of the array is between 1 and 100,000, and each element in the array lies between -10,000 and 10,000. These constraints emphasize the importance of creating an efficient algorithm to handle large input sizes. Finally, let's discuss some edge cases that we need to be mindful of. First, when the array contains all negative numbers, such as -2, -3, -1, -4, the maximum subarray would consist of the single largest number, as including additional numbers would only decrease the sum. Second, if the array has only one element, like 0 or -5, the result would simply be that element. Third, when the array has all positive numbers, like 1, 2, 3, 4, the maximum subarray would be the entire array. Lastly, when the array alternates between positive and negative values, like -2, 3, -1, 4, -5, 2, the algorithm must carefully decide where to separate subarrays to ensure the sum is maximized. These scenarios highlight the need for a robust approach that works in all cases. To solve the maximum subarray problem, the goal is to find the contiguous subarray within an array nums that yields the largest possible sum. One of the simplest methods to approach this is the brute force strategy. In this approach, we examine every possible subarray by iterating through all potential starting points in the array and, for each starting point, calculating the sum of all subarrays ending at different positions. While this method ensures we eventually find the maximum sum, it is computationally expensive. With a time complexity of n squared, this approach becomes inefficient for larger arrays because we essentially process each subarray multiple times. On the positive side, it uses O(1) additional space since no extra data structures are involved. However, its quadratic time complexity makes it impractical for larger datasets, and thus, we need a more optimal solution. To address the inefficiencies of brute force, we can use Cadon's algorithm, which leverages a greedy approach to achieve optimal performance. The key insight here is that we can maintain a running sum as we traverse the array, and if this running sum ever becomes negative, it won't contribute positively to any further sums. Therefore, we reset it to 0 when it turns negative. The algorithm is straightforward: initialize two variables, current_sum set to 0 and max_sum set to -infinity. For each element in the array, add it to current_sum, update max_sum to the higher value between max_sum and current_sum, and reset current_sum to 0 if it becomes negative. This method is incredibly efficient, requiring just one traversal of the array, resulting in a time complexity of O(n). It also uses only two variables, making it space efficient with O(1) space complexity. By avoiding redundant calculations, Cadon's algorithm is ideal for solving this problem efficiently, even for large inputs. Another approach to solving the maximum subarray problem is the divide and conquer method. Here, the array is recursively divided into two halves. To find the maximum subarray sum, we compute the maximum subarray within the left half, the right half, and any subarray that crosses the midpoint of the array. The solution is the maximum of these three values. This approach has a time complexity of O n log n, because at each level of recursion, we process the array in O n time, and there are log n levels of recursion. However, the space complexity is O log n due to the recursion stack. While this method is elegant and more efficient than brute force, it is slower than Cadon's algorithm due to the overhead introduced by recursion. This makes it less favorable when compared to the greedy approach, especially for large arrays where performance is critical. Ultimately, Cadon's algorithm is the optimal solution for the maximum subarray problem. It was chosen for its efficiency, simplicity, and practicality. With a linear time complexity of O n, it is significantly faster than both the brute force and divide and conquer methods. Its straightforward implementation requires minimal extra space, using only two variables to track the running sum and the maximum sum. The algorithm also incorporates key observations that make it highly effective. A subarray with a negative sum is reset to 0, as it cannot contribute positively to the result, and by maintaining the running maximum, we ensure the best result is always readily available by the end of the traversal. While the brute force method is too slow and divide and conquer adds unnecessary complexity, Cadon's algorithm strikes the perfect balance between performance and simplicity, making it the ideal choice. In both competitive programming and real-world scenarios, Cadon's algorithm stands out as the most reliable and efficient solution for the maximum subarray problem. By ensuring optimal performance with a time complexity of O n and requiring minimal additional space, it meets the demands of even the largest datasets. Its simplicity in implementation further highlights its advantage, as it avoids the complexity of recursion or nested iterations. For these reasons, Cadon's algorithm is not only the preferred method for this problem but also a cornerstone technique in solving a variety of optimization problems in arrays. The maximum subarray problem asks us to identify a contiguous subarray within a given array nums that has the highest possible sum. For instance, in the array -2, 1, -3, 4, -1, 2, 1, -5, 4, the subarray 4, -1, 2, 1 yields the largest sum, which is 6. To solve this efficiently, we use Cadon's algorithm, which applies a dynamic programming approach with a time complexity of O n. The algorithm revolves around maintaining two key variables, current_sum, which tracks the sum of the ongoing subarray, and max_sum, which records the highest sum encountered so far. We start by initializing max_sum to the smallest possible integer value, ensuring it can capture any subarray sum, and set current_sum to 0. These initial values set the foundation for iterating through the array and dynamically updating our results. Next, as we iterate through the array, we process each element, updating current_sum by adding the current element, number. If current_sum becomes negative at any point, we reset it to 0. This is because a negative sum will only reduce the potential maximum sum of any future subarray, so it's better to start fresh. Concurrently, we update max_sum to be the higher value between its current value and current_sum. This ensures we are always tracking the largest sum encountered so far. Additionally, the algorithm naturally handles edge cases, such as arrays with all negative numbers, by ensuring max_sum updates to the largest single element before resetting current_sum. Once the iteration concludes, max_sum contains the maximum subarray sum, which we return as the result. There are some important insights behind Cadon's algorithm. First, resetting current_sum to 0 when it goes negative ensures that subarrays with a detrimental impact are discarded. This makes the algorithm efficient at identifying the optimal subarray. The variable max_sum plays a crucial role in ensuring that the highest sum is always preserved, even if the largest subarray sum occurs in the middle of the array. Furthermore, this approach is highly efficient, requiring only a single pass through the array, which gives it a time complexity of O n. It also has a space complexity of O 1, because it uses only two variables, current_sum and max_sum, without any additional data structures. The algorithm relies on two simple variables, current_sum, which tracks the ongoing subarray sum, and max_sum, which records the global maximum sum. No additional data structures are required, as the algorithm operates directly on the input array. While Cadon's algorithm is already optimized for both time and space, there are a few ways to improve clarity. For example, you can use inline conditionals to simplify the logic for resetting current_sum. Additionally, explicitly handling edge cases, such as empty arrays, before applying the algorithm ensures robustness and prevents errors. There are a few edge cases to consider. If the array contains only negative numbers, the algorithm will correctly return the largest single element, as max_sum will update to the maximum negative value. For single element arrays, the algorithm simply returns that element as the maximum sum. For an empty array, the behavior depends on the problem constraints. The algorithm should either return 0 or an appropriate error message. Let's examine an example with the input nums equals -2, 1, -3, 4, -1, 2, 1, -5, 4. This input will allow us to see how the algorithm processes each element step by step to arrive at the maximum sum. Here's how the algorithm executes for the given input. Initially, max_sum is set to -infinity and current_sum is 0. As we iterate through the array, we first encounter -2, setting current_sum to -2 and updating max_sum to -2. The next element 1 resets current_sum to 1, which becomes the new max_sum. For -3, current_sum drops to -2, but max_sum remains 1. With 4, current_sum increases to 4, and max_sum is updated to 4. As we progress, -1 reduces current_sum to 3, but max_sum stays at 4. Adding 2 raises current_sum to 5, and then 1 brings it to 6, updating max_sum to 6. After encountering -5, current_sum drops to 1, but the final 4 brings it back to 5. The iteration ends with max_sum at 6, which is returned as the result. This process demonstrates the algorithm's O(n) time complexity and O(1) space complexity, making it both fast and efficient. This implementation solves the maximum subarray problem using Cadon's algorithm, which is efficient with a time complexity of O(n). The function maxSubarray takes a list of integers nums as input and returns the maximum sum of any contiguous subarray. The algorithm begins by initializing two variables, current_max and global_max, both set to the first element of the array. These variables are used to track the maximum subarray sum ending at the current index and the overall maximum subarray sum encountered so far, respectively. The loop starts at the second element, index 1, and iterates through the array. For each element, the algorithm decides whether to include it in the existing subarray, by adding it to current_max, or to start a new subarray with the current element alone. This decision is made using the max function. After updating current_max, the algorithm checks whether this new subarray sum is greater than the global_max. If it is, the global_max is updated to this new value. At the end of the loop, global_max contains the largest sum of any contiguous subarray in the input list. This approach ensures that each element is processed only once, making it highly efficient. It also handles edge cases, such as arrays with all negative numbers, where the maximum subarray would consist of the single largest, least negative, element. This is the Java implementation of the maximum subarray problem. The logic mirrors the Python implementation, using a single pass through the array with variables to track the current running subarray sum, current max, and the maximum sum found so far, global max. Key differences include Java's explicit type declarations and the use of the math.max function for comparisons. The solution maintains O(n) time complexity, as it iterates through the array once, and O(1) space complexity, as no additional data structures are used. To solve the maximum subarray problem, we begin with an example array that includes both positive and negative numbers, nums equals -2, 1, -3, 4, -1, 2, 1, -5, 4. The goal is to find the contiguous subarray with the largest sum. First, we initialize two variables, current_max and global_max. Both are set to the first element of the array, which is -2. We then proceed to iterate through the array starting from index 1. At index 1, the value is 1. We calculate the maximum between this value and the sum of the current underscore max plus this value. This gives us a new current underscore max of 1. Next, we update global underscore max as the maximum between the previous global underscore max and the new current underscore max, which results in a global underscore max of 1. Moving to index 2, the value is -3. Again, we compare -3 with the sum of current underscore max plus -3. The maximum here is -2, so current underscore max becomes -2. Since global underscore max remains higher at 1, it does not change. At index 3, the value is 4. We calculate the maximum of 4 and the sum of current underscore max plus 4, which results in a new current underscore max of 4. This also updates global underscore max to 4. Now at index 4, the value is -1. We calculate the maximum between -1 and the sum of current underscore max plus -1, which results in a current underscore max of 3. However, global underscore max remains unchanged at 4 since it is still greater than current underscore max. At index 5, the value is 2. Here, the maximum of 2 and the sum of current underscore max plus 2 is calculated, yielding a new current underscore max of 5. This updates global underscore max to 5, as it now exceeds the previous value. At index 6, the value is 1. Adding this to the current underscore max of 5 gives us 6, which is greater than 1. Therefore, current underscore max is updated to 6, and global underscore max is also updated to 6. At index 7, the value is -5. The maximum here is calculated as -5 or 1, resulting in a current underscore max of 1. Since global underscore max remains higher at 6, it does not change. Finally, at index 8, the value is 4. The maximum of 4 and the sum of current underscore max plus 4 is calculated, giving a current underscore max of 5. However, global underscore max remains 6 as it is still the highest value encountered. After iterating through the entire array, the final value for global underscore max is 6. This represents the largest sum of any contiguous subarray within the input array. Moving to another example, consider an array consisting entirely of negative numbers, nums equals -1, -2, -3, -4. Here, we once again initialize current underscore max and global underscore max to the first element, which is -1. The goal remains the same, to find the maximum sum of a contiguous subarray. Starting the iteration at index 1, the value is -2. We calculate the maximum between -2 and the sum of current underscore max plus -2, which results in a current underscore max of -2. Since global underscore max is still greater at -1, it remains unchanged. At index 2, the value is -3. The calculation here results in a current underscore max of -3, and global underscore max remains -1. At index 3, the value is -4. The maximum of -4 and the sum of current underscore max plus -4 gives a current underscore max of -4. Throughout this process, the global underscore max does not change and stays at -1. As the array contains only negative numbers, the least negative value, -1, is the largest sum of any contiguous subarray. Now consider an input array with all positive numbers, nums equals 1, 2, 3, 4. Here, we begin by initializing current underscore max and global underscore max to the first element, which is 1. At index 1, the value is 2. Adding this to the previous current underscore max of 1 gives us 3, which is greater than 2 alone. So, current underscore max becomes 3, and global underscore max is updated to 3. At index 2, the value is 3. Adding this to current underscore max results in 6, which is larger than 3. Thus, current underscore max is updated to 6, and global underscore max becomes 6. At index 3, the value is 4. Adding this to current underscore max gives 10, which is the new maximum. The final update to global underscore max is 10, which represents the largest sum of any contiguous subarray within the input array. With all positive numbers, the entire array itself forms the subarray with the maximum sum. These examples illustrate how the algorithm dynamically computes the largest subarray sum using the sliding window approach, efficiently tracking the maximum sum at each step. To analyze the time complexity of the algorithm,
we start with the initialization step.
Here, we assign the first element of the input array nums to two variables, current_max and global_max. These are simple assignments and take constant time, or O1. Next, the algorithm iterates through the array starting from the second element. For each iteration, two operations are performed, updating current_max and updating global_max. Both of these involve comparisons using the max function, and each comparison takes constant time, O1. Since the loop processes each element exactly once, and there are n elements in the array, the total time for the iteration is O(n). Finally, returning the result stored in global_max is another constant time operation, O1. Adding these steps together, the time complexity of the algorithm can be calculated step by step. Summing up the initialization, iteration, and return steps, we get O1 for initialization, O(n) for iterating through the array, and O1 for returning the result. This gives us a total time complexity of O(n), as the O(n) term dominates. Now, looking at the space complexity, the input array nums is passed into the function, but it is neither modified nor duplicated, so no additional space is used for storage. The algorithm uses two auxiliary variables, current_max and global_max, to keep track of intermediate results. Each of these variables requires O1 space. Moreover, no additional data structures, like arrays or stacks, are used in this solution. Therefore, the space complexity is determined solely by these variables, making it O1. When we sum up all space-related components, the total space complexity of the algorithm remains O1. To highlight the efficiency of this approach, let's compare it with the brute force method. In the naive solution, we would check all possible subarrays of the input array and calculate the sum for each to find the maximum. With n elements, there are O(n²) possible subarrays, and calculating the sum of each subarray takes O(n) in the worst case. This results in a total time complexity of O(n³). However, the brute force approach still has a space complexity of O1, as no additional data structures are used. In contrast, Cadon's algorithm achieves a significant improvement by reducing the time complexity to O(n). It avoids redundant calculations and maintains running sums efficiently with a single pass through the array. The space complexity remains O1, as it only uses two variables. Looking at the best, average, and worst cases, the time complexity of Cadon's algorithm is consistently O(n). This is because the algorithm always iterates through the entire array, regardless of when the maximum subarray is found. In all scenarios, whether the maximum is at the beginning, middle, or end, the algorithm performs the same single pass through the array. The space complexity also remains O1 in all cases since no additional memory is required beyond the two variables. In conclusion, Cadon's algorithm is highly efficient compared to the brute force approach. Its time complexity of O(n) and space complexity of O1 make it an optimal solution for the maximum subarray problem. By leveraging a greedy approach and avoiding redundant calculations, Cadon's algorithm ensures both time and space efficiency. When tackling the maximum subarray problem, there are a few common pitfalls to watch out for. First, some people confuse subarrays with subsequences. Remember, subarrays must be contiguous sections of the array, whereas subsequences can include non-contiguous elements. If you try to select non-contiguous elements when solving this problem, you'll violate the constraints. Another mistake involves handling negative numbers. It's easy to assume the maximum sum will always be positive, but that's not true. For arrays consisting entirely of negative numbers, the solution is the single least negative element. Lastly, edge cases often trip people up. For instance, a single-element array, an array with all negative numbers, or arrays containing a mix of zeros, positives, and negatives. Make sure to test these scenarios thoroughly to avoid runtime errors or incorrect results. Another common issue arises when using a brute force method. If you recompute the sum of subarrays repeatedly with nested loops, it drastically increases the time complexity, making your solution inefficient for large arrays. Instead, aim to optimize the calculation to avoid redundant work. Additionally, improperly initializing variables can lead to subtle bugs. For example, if you initialize the maximum sum to 0 rather than the first array element, your solution might fail for arrays where all elements are negative. On the topic of interviews, Cadon's algorithm is the gold standard for solving this problem efficiently, with a time complexity of O(n). It maintains both the current maximum subarray sum and the global maximum sum, and you should be prepared to explain its mechanics clearly. Interviewers might also challenge you with follow-up questions, such as modifying Cadon's to track the subarray indices or extending it to solve a 2D matrix version of the problem.
Optimizing space usage is another key consideration.
While Cadon's algorithm only requires O(1) space, some solutions unnecessarily store the sums of all subarrays, which is inefficient. Be prepared to discuss and contrast such approaches in terms of their space complexity. Additionally, the maximum subarray problem has several related problems you may encounter. For example, LeetCode 918, the maximum sum circular subarray, requires incorporating the circular nature of the array into your solution. Another is LeetCode 121, best time to buy and sell stock, which is conceptually similar to Cadon's algorithm but applied to a single transaction in stock trading. Other variations include LeetCode 152, the maximum product subarray, which involves products instead of sums. Understanding these related problems can help you spot patterns and apply similar techniques in different contexts. Finally, let's explore alternative approaches and their trade-offs. The brute force approach involves checking all possible subarrays and computing their sums, which is simple to implement but highly inefficient with a time complexity of O(n squared, or even O(n cubed). For a more efficient but slightly more complex solution, there's the divide and conquer approach, which divides the array into two halves, recursively finds the maximum subarrays in the left and right halves, and combines the results. This method has a time complexity of O(n log n, but can be slower in practice due to recursion overhead. The most efficient solution is Cadon's algorithm, which uses dynamic programming to achieve O(n) time complexity. It keeps track of the maximum subarray ending at each index and the global maximum, all while using constant space. While Cadon's is optimal, it requires a solid understanding of dynamic programming concepts to implement and explain effectively. Each approach has its strengths and weaknesses, and understanding them will help you tackle variations of this problem confidently.
Great job!
In this session, we explored the maximum subarray problem and solved it using Cadon's algorithm. Remember, mastering efficient algorithms like this is essential for coding interviews and real-world problem solving. Stay tuned for more tutorials, and keep practicing.
See you in the next session. That's the end of this tutorial.
I hope you found this explanation helpful for understanding the solution to this LeetCode problem.
If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions.
Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have.
Thanks for watching, and happy coding!